Okay, this is video number 4 for a unit that we're doing that comes from several spots in our textbook, A5 and A6, which are the supplementary sections in the back, and then 2.7 in the main part of the textbook. The first example for today, the instructions are: solve the inequality by graphing, confirm your solution algebraically, and this is our problem of interest for number 1 here. I'm actually going to take the reverse approach. I want to do the algebraic approach first, and then after that, we'll take a look at how this plays out graphing. All right, in the interest of time, I already worked out all the steps here, so we'll just run through what needs to happen to get this thing solved algebraically. Right, so x squared minus 5 inside of absolute value less than or equal to 4. Well, some stuff that we know, whether that's an equals or an inequality symbol, if it's an absolute value, we have to split this into two something, either two equations or two inequalities, depending on the nature of what we're given. Right, the pattern for the split, actually, I'm sorry, we have to make sure that's isolated, and we can do the split. This was already isolated. Okay, so the pattern for the split for an absolute value inequality is what's inside the absolute value, same direction, same sign. What's inside the absolute value, flip the direction of that inequality symbol, change that sign. We need a connecting word in the middle. If it's a less than, we're always dealing with an and the way I remember that is you can kind of spell and with an inequality symbol. And the other one, or the other possibility, would be if it was a greater than instead of a less than, you could spell greater with or. So in this case, because it is a less than, the connecting word is an and. Right, each of these guys need to be solved independently from one another. So looking at the one on the left, we're going to want to get that 4 over there, subtract it from both sides, gets us to here. That is a difference of 2 squares, factors into x plus 3, x minus 3. So this hits one of our intermediate goals. We want to get everything factored on one side, 0 on the other. Make sure you check, did that arrow need to flip or not? Addition or subtraction never flips it. Factoring one side would never flip it. If we traded sides of the inequality, multiplied both sides by negative or divided both sides by negative, then that arrow would have to flip. All right, now what makes this thing true? For this one, what I chose to do was use the test intervals. So I know x plus 3 is 0 at negative 3. X minus 3 is 0 at 3. This is negative to the left of negative 3, positive to the right. Same story here and here. We're looking for a less than, so that means we're multiplying two things together where the sign's different. So we are looking at the interval, negative 3 to 3. You have the equal sign underneath, so that means we want those endpoints of negative 3 and 3. They cause it to actually equal 0. So this solves the left half of our problem. Okay, now on to the right half. We're going to add the 4 over, factor that side, and then set up the test intervals. So x plus 1 is 0 at negative 1, negative to the left, positive to the right. X minus 1 is 0 at 1, negative to the left, positive to the right. We're multiplying two things together, and we're interested in when is it greater than 0. Well, it's going to be positive when the signs are the same. We're talking there and there. We are including the endpoints. So we get the closed brackets there and there. Now back to the big picture. When we first split this up, we need to know what makes this true and that true both at the same time. Now, it may not be obvious, or you may have difficulty visualizing, well, what makes that and that true at the same time? So what we can do is take a little bit more of a visual graphing approach to wrapping this problem up. We know that this would represent the numbers between -3 and +3 inclusive. This would represent less than or equal to -1 or greater than or equal to +1. And then the connecting word "and" means where do those guys overlap? Here and here. That gives us the final solution set. We're looking at a number line graph. It would look like this. In terms of writing it out with interval notation, it would look like that. So the solutions are -3 to -1 inclusive, or the union means the same thing as an or, 1 to 3 inclusive. So that's one way that this problem could play out, solving it algebraically. All right, now what about taking a graphical approach? So what I'm going to first do is take a look at, well, what does that look like if we graph it in an xy plane? So what does y equal to the absolute value of x squared minus 5 look like? Well, I'm going to start with the x squared minus 5 part. So we know this guy in here, not worrying about the absolute value just yet, it's a basic parabola bumped down 5 units. So using the vertex as a point of reference, going down 1, 2, 3, 4, 5, puts us here. The coefficient of the squared term is 1, so it's considered to be standard width. So we can go over 1 up 1, over 1 up 3, over 1 up 5, and the next one's probably not going to fit. It's up there somewhere. Mirror image on the other side. So before we take into account the absolute value part, we are looking roughly like that. Now, the absolute value is going to take the stuff below the x-axis and reflect it above the x-axis. Or the y values that are negative become positive. That's what absolute value does. So that's 1, 2, 3, 4, 5. 5 passed. 1, 2, 3, 4, 5. These guys here, 1, 2, 3, 4. 1, 2, 3, 4. There and there. 1, 1. So now what we end up getting after the absolute value is something that looks like that. So let's give that a quick highlight just so, I don't know how well this comes out on the video. Now what I'm going to do is graph the right-hand side in an xy plane. So what does the graph of y equal 4 look like? Well, it's just a horizontal line at 4. Give that a quick highlight. And now, big picture. How do these guys connect together? Well, we're looking for when is this less than that? Well, in an XY graph, that's asking the same thing, is when is this graph below that graph? Well, where is the orange graph on the left less than the pink graph on the right? So that's happening here and here. That's when the orange graph is below the x graph. So at what x values is that occurring? 1, 2, 3. -1. We are interested in 0, so endpoints get included. And over here from +1 to +3. It's a union of those two sets. Let's take a look at what we did earlier. See if we can get this all on one screen. Slide something out of the way here. All right, so our algebraic solution, our graphical solution, and you can see that they're both the same. All right, so which is better, which is worse? For this particular problem, it seems to me that this purely graphical approach was a little more efficient than this. Now, that's not going to be true for all of these types of problems. It happened to work out that way for this one. One of the things hopefully you've picked up on and will continue to pick up on is that feel of, well, what's going to work best when? You need to have both skill sets. There are problems where the graphical approach really wouldn't work very well. And that would happen in a case where if these weren't very clean intersection points, if they didn't cross at lattice points, we would need to go through some sort of process like this to be able to get accurate solutions. So when this does work out cleanly, it's to your advantage to be able to deal with it that way. But you also still need to have this skill set to get to solutions in certain situations. All right, that wraps up question number 1. Question number 2 from today's handout. So we have the same set of instructions. They're telling us to solve it by graphing and confirm it algebraically. I prefer the flip of those two. As long as you have both skill sets coming away from this unit, it doesn't really matter which one you decide to do first, which one you decide to do second. All right, again, in the interest of time, I already worked out the algebraic set of steps here, so we can get through this a little quicker than writing everything out by hand. So your thought process from the top. As soon as you see you have an absolute value inequality or an absolute value equation, your thought process is that guy's got to be isolated and we need to split. Okay? It's not going to happen in terms of getting the correct answer if you don't start off with those two things right there. All right, so this is already isolated, so we can jump right to the split. So for an inequality, rule for the split is what's inside the absolute value, same direction, same sign. What's inside the absolute value, flip the arrow, and then you have to change the sign since that's got more than one term. Ultimately, that negative sign has to be multiplied through. We need a connecting word. If that was a less than, we would use an and. If it's greater than, we use an or. And we can remember it in terms of great or. All right, these two guys get solved independently of each other, and then in the end, combine them together with the or. So focusing on the left-hand side, the first thing I did was I flipped sides of the inequality. I'm going to ultimately want to end up with the factored side on the left and the 0 on the right-hand side. So one way to make that cleanly happen is I want my square term over on the left. So that's one of the things that would cause the direction of the arrow to flip. If you trade sides of the inequality, like I did here, or if you multiply both sides by a negative, or if you divide both sides by a negative, the arrow would flip. Okay, next move is that x needs to come over, the 1 needs to come over to get 0 on that side. That gets us to here. Next is that needs to get factored. That gets us to here. And now we hit the intermediate goal, which is to have a completely factored 0 on this side. Did a little test interval here. X minus 4, 0 at 4. X plus 1, 0 at negative 1, negatives to the left and positives to the right. This is a less than, which means we're multiplying two things together to produce a negative number. That's going to happen when signs are different. We don't have the little equal sign underneath, so we're not interested in endpoints. We're interested from negative 1 to positive 4 uninclusive. Okay, right-hand side. Put this back up here. So from here to here, clear out those parentheses by multiplying through by a -1. That does not flip the arrow. We didn't multiply both sides by -1. We're just working on one side of the inequality. Simplifying one side of the inequality is never going to flip that, whether it's multiplying through by a negative number or not. Okay, next move is all this stuff over to the left. -x squared comes over here, becomes +x squared. Subtract the 2x from both sides, subtract the 3 from both sides. Now we're here. Factor the side with all the stuff. Do our test interval thing. X minus 2, 0 at 2. X plus 1, 0 at -1. Negatives to the left, positives to the right. Once again, we have less than. Multiplying two things together to produce a negative number means signs must be different. So we're looking at the interval from -1 to 2, uninclusive, because we do not want 0 as part of the solution set, just less than 0. Okay, now back to the big picture. This or this. So taking a look at the number line graph here, -1 to 4, looks like that. -1 to 2, looks like that. There's 2 there. Oops, actually, you should have gone a little bit further to here. It turns out that's not going to affect our final answer, but it's still a mistake. Now, or is combining those two graphs together. We're taking all of this stuff, putting it together with all of this stuff. Well, all of this is already in there. So this is our final answer. That doesn't add anything more to the solution set. So our final answer is from -1 to 4. Right there. So again, this arrow here, although I'm not justifying making an error, didn't affect the final answer of -1 to 4. All right, so that's one way to get to the final answer using an algebraic approach. Now on to the graphing approach. So what we're going to do is we're going to graph the left-hand side in an xy plane. Y is equal to the absolute value of x plus 1. Well, we know that the absolute value of x is that parent function right there. That plus 1 slides that graph 1 to the left. So the vertex of that guy is going to be at 0, -1, 0. And then it's going to go up this way with a slope of +1. And then up the other way with a slope of -1. And it looks like this. Okay, now, I'm going to do the same thing with the other side. We're going to get a graph of y is equal to x squared minus 2x minus 3. So one way we could do that is we could identify the vertex by the opposite of b over 2a. So that's going to be a +2 over 2 times 1. 2 over 2 is equal to 1. So we know the x coordinate of the vertex is at 1, comma something. We can plug that 1 back into the original expression. 1 minus 2 minus 3. -1 minus 3, -4. So we are at 1, -4. All right, next place we could go is the fact that this is standard width. So we can do over 1 up 1, over 1 up 3, over 1 up 5, and then the next one will be up here somewhere. Mirror image on the other side of the axis of symmetry. So I actually lost track of where we were up here. 1, 1, 2, 3, 4, 5. So it's actually right there. So 1, 2, 3 to the axis of symmetry. 1, 2, 3 past. Looking like this, crossing that point. So let's color code this here. So y is equal to the absolute value of x plus 1. That was this here. Y is equal to x squared minus 2x minus 3. That's this guy right here. And they're asking us, where is the absolute value bigger than a parabola? Or where is the orange graph over the pink graph? Where the y values of the orange graph bigger than the y values of the pink graph? Well, that happens in here. This area right here is where the pink graph is below the orange graph. So it appears as though that's going from -1 to 4. We do not want endpoints included because we don't have the little equal sign underneath, so those are open parentheses. All right, let's compare this to the algebraic approach that we did a few moments ago. So we know from the algebraic set of steps that we got -1, 4. There's the same -1, 4. All right, emphasizing the importance of, in this unit, you need to have both tools in your toolbox. There are certain problems that need to be done algebraically. They don't lend themselves very well to the graphical approach. In contrast, if you are doing everything algebraically, you'll have a hard time getting through your typical assignment or assessment that involves this stuff. You need to be able to recognize where is the graphical approach going to be a little bit more efficient. All right, so that is it as far as today's lesson goes. This lesson more or less reviews most of what we've talked about from this little unit covering the sections we talked about earlier. If you can do these problems, you're in pretty solid shape in terms of knowing all the little steps that led up to this.